welcome. Here we are. Take a few moments to make sure the stream is working, and we'll get going onto programming exercises for the day. I don't know how long I'm going to work today, maybe 10 hours or so. Try to spend some time. Today, maybe 10 hours or so. Yeah. Try maybe go like 10 hours. I could try. See how far I get. It's 11:30 now. It would be like 11:30 a.m. So it's 11:30 p.m. I want to go to, which would be like 23, 10 hours, no, it would be 10 hours. So it'll put me at 21:35, which is also 9:35. Okay, let me get into, this question is last stone weight 2. So yeah, try to go till I get to 21:35 here. I'll maybe take an hour somewhere in between break. See how far I can get through these questions. Look at this. I had, just those of you interested, in preparation for, I think I mentioned I was going to work on another project. It's actually related to CPUs. I noticed something about Wikipedia that if you try to go through one page, there are so many hyperlinks to other things that if you use a breadth first search, look at all these other links that you end up queuing up to look through. But anyway, yeah, that's another project I want to work on. It's not the more immediate project I'm working on now, but kind of splitting my time between a few things. But yeah, I do want to get through my actual interview questions too. I could probably do quite a few very quickly, I think. Anyway, that wasn't even related to building the application software, so that way it's easier to apply. Anyway, so last stone weight 2, you're given an array of integer stones where stone of I is the weight of the ith stone. We are playing a game with the stones. On each turn, we choose any 2 stones and smash them together. Suppose the stones have weights x and y, with x less than or equal to y. The result of this smash is, if x equals y, both stones are destroyed, and if x is not equal to y, stone of weight x is destroyed, and the stone of weight y has new weight y minus x. Okay, so x is the lower weight. Okay, that's fine. At the end of the game, there's at most 1 stone left. Interesting. Return the smallest possible weight of the left stone. If there are no stones left, return 0. I think you just end up with the maximum. What's the acceptance rate on this? That's kind of low. Not a lot of submissions. Maybe this is harder than I realize. 30 stones between 1 and 100. I would suggest 1 stone left. Return the smallest possible weight of the left stone. If there are no stones left, return 0. Oh, okay. Oh, I see. At most 1. Okay, got it. I thought it said at least. I thought it said 1, not at most 1. Okay, could be 0 or 1 left. All right. Interesting. And any 2 stones, let's smash them together. And we want the smallest possible weight is if there are no stones left, I'm assuming in some cases, so like we could just smash everything against 8, and there will be a stone. So I think if it's possible to remove all the stones, then we return 0, right? Can they give me an example where return 0? This is an interesting question. I have to think about it a little bit more. Let me see. 1, 1, 2, 2. You could smash this one and this one, and you're left with a 1. You could smash this one, and this one, and then these 2 together. Smash these 2, smash this one. What about this? These 2 cases. What am I supposed to get? So I think I'm allowed to pick any sequence of smashing things together. So quote unquote smash. Let's say any sequence of any pairs I could pick. I want to pick. So here it should be 1, and here it should be 1. Okay, so I think you only return 0 if it's not possible. So if they're all 2s, for example, you return 0. no sequence of pairs selected can give you, oh wait, oh yeah, no, excuse me, no, never mind, you don't get 0 here. You have to select 2, and then you can't select 2 after that. What about this one? Oops. Try to just understand what they're asking exactly. So here, no matter what you do, if you pick 2, you end up, okay, so interesting. So there are different ways of analyzing games. One is to just basically emulate the game, and you can use states, game states, if you wanted to. So one way of doing this would be, like, you could have, for example, case 6, you have like a game state of 2 and 2, which gives you end up with 0, right? And so you could say maybe going backwards, starting from 0 stones, how many states could there possibly be, right? And the number of states going back from 0 would be basically all of the final stones that are possible that give you pairs, right? Equal pairs, right? So like in case 1, there's really only 1 and 1 from 0. The other end state, so there's 2 end states. That's one end state is empty, and that would have to be preceded by 1 1, and nothing else, right? That's only the duplicates could be that state. The other end state is just a single stone, which all of these could be the last stone in theory. Now, then from having a 1 and 1, then you would say, okay, you have to have destroyed some stone to end up at 1 1, right? So which stone could have been destroyed to get you to 1 1? Well, I would suggest maybe you would have to have destroyed something, either 2 things together and they're gone now, or it would have to be something that resides, that's left over, right? But the problem is that 1 1, when something is destroyed, there's nothing that gets you to state 1 1. In other words, if you go backwards from 1 1, there's no state. So not only does that stop there, sort of that, you maybe think of it as like a graph, that becomes a disconnected component of the graph, and it never gets back to this initial state. So that whole part of the graph could be ignored. So it'll never be 0 in that case. Because you'd have to, in order to get to that state that got you to 0, basically you'd have to have any state that can get to 1 1 would have to have 1 other stone present, and in fact it would have to have 2 stones present. There'd have to be 1 other stone, and it'd have to be something was destroyed to get there. So there'd have to be either 1 more stone or 2 more stones. 2 more stones requires a duplicate, which there you don't have another duplicate, and 1 more stone. I think it always has 2 stones actually. Yeah. Is it? Because either 2 stones are destroyed or 1 stone is destroyed. So you either get doubles of something, which you don't have, or you have to have 1 more stone. But the problem is that the other stone, if you smash it with either of the 1s, that stone will be present, that stone will be gone, because the 1s are the smallest element. I'm trying to think if there was like something else here. If there was like another 1, you couldn't do it with another 1, actually. That wouldn't work either. So if you had something like, maybe another case would be a little easier to think about, like 3 and 3, or yeah, 3 and 3. Yes, 3 and 3, you could have another stone. You can go 0 0 0, no stones, to 3 and 3. Then you can go to 2 3 3, because you could smash 3 and 2 together. So that's a state that would work, right? So it doesn't. There's no state to look at here. But then from 2 3 3, then you got to wonder, okay, I think 2 is the. Well, no. Can you smash 8 at all? What does case 1 give you? 0? 1. Anything you pick with 8 is going to destroy the stone, right? Is it the smaller stone that remains or the larger stone? X is less than or equal to Y. Oh, okay. The new stone loses that weight. Oh, okay. Okay. I see. I see. Okay, I missed that part too. That's important as well. So the reason why you get 1 here is you can take 8 and 7, put them together and get a 1. Oh, okay. It's a little more complicated than I thought. This is a little more complicated than I thought. I was gonna say, I was like, I think if it's you just get the largest stone is always the one that's left, right? But that gets smaller each time. Okay, it's a little more involved. Yeah, I was thinking in that case, it's always just gonna be the maximum stone you have. It's just always gonna be what's left. Okay, well, in that case, you can actually, I think, take a summation here. Because if you take the total amount here, any combination of things, whatever stone you pick is going to be subtracted from the total, right? This is interesting. Yeah, I gotta think about this a little bit more now. What I suggested before, I think, with like making it sort of like a game type of thing and using states, maybe not as meaningful here. Well, you could still use that approach. It's just you gotta have to like wonder about the main issue you run into is what are the time bounds you end up with. I think you end up with quadratic time with something like this, but there maybe are a lot of possible states, so that's like one approach. You could probably use that. If there are 30 stones, how many possible states could you have? Well, basically, it's any like 30. It's actually 2 to the 30th. That's a billion different states, I think. And the reason it's 2 to the 30th is it's any subset of the states of the stones is a potential state, and the sum of all of the possible subsets is exactly the power set, size of the power set, which the power set is 2 to the 30th. Yeah. Every possible subset is a potential state. Question is, how many of those states are actually going to be there, right? Like how many of those states you actually need to worry about or be concerned yourself with? I don't know. I think there's probably a greedy approach to this, or maybe some kind of a shortcut. Either a DP, greedy approach, 2-pointer, maybe a binary search of some sort. Something. You could use, as I mentioned, the sort of game, create a graph out of the states in the game and then walk the graph kind of a approach. You could always do that with a game. You do that with a lot of problems, but I think in this case there are potentially a lot of states involved. Yeah, these array-based questions with stones are like quite challenging, in my opinion. Always really make you think. All right, well, there's a quadratic number of options from this state, right? And you always lose 1 stone. And you could just say of those states, yeah, I mean, if you just use like straightforward recursion and backtracking, I don't know how difficult this will be if you do that. It's definitely a billion different operations is kind of a lot. So I'm not sure if that's the way to go. It's probably a shortcut of some kind, but trying to solve for this question, maybe you can do 7 and 8 gives you 1, 3 and 3 gives you 0, 4 and 2 gives you 2, 2 and 1 gives you 1. That's one way to get 1. You only get 0 if any possible maneuver will end up with 0. So you could check that directly. You could just pick, you could just go straight through. It only returns 0 if any maneuver gives you 0. If every maneuver gives you 0, any maneuver. So you could check that pretty easily, actually. If you just pick a random maneuver and you get 0, then that's it. Is that true? Is it possible to get a value? That's actually a good question. So the things that return 0, I think every possible way you could do it returns 0. So you could just check if one of these ways gives you 0. Alternatively, if there's any way that doesn't give you a 0, then obviously it's not 0. In that case, you have to check that every way doesn't give you, yeah, I don't know. Actually, no, it's the other way around. You have to prove that any approach you take, which there's a lot of different approaches, any approach you take is always going to give you 0. I think that just I think you've got to have an even number of stones to have 0, and I think you just need to have. I'm not sure. I gotta come find a proof for that. I think. I'm not sure about this one. I don't know. What about this? You can get 0 with this, but you could also probably get something else too. Oh, okay. What if you did like 3 and 2 gives you 1, and then 3 and 2 again would give you 1 again, and then 1 and 1 gives you 0. Is that it? If it's just an even number of each frequency? Yeah, there's something. There's something here. I'm sure there's a way to do this more efficiently. This gives you 0. Okay. So this one gives you 0 also. The sum is 14. Subtract 4, you get 10. Subtract 6, you get 4. Subtract 4 and 4. 2 and 3 give you 1. 3 and 4 gives you 1. 2 and 1 gives you 1. I don't know what to say. I don't know. Oh. I don't know. Oh, geez. They all give you 0. What? 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 No. How do I not get 0? Is it possible for me to not get 0? What? What is going on? Huh? I don't know what's happening here. I think if there are any duplicates, it goes to 0. Is that it? Yeah, I don't know. This is an interesting question. I don't know what to say. I don't know how those will end up at 0. I don't know. What is going on? What is happening? Okay, these are even, the sums. That's definitely, I think it's part of it. These are odd. I get a 1. Gee. Huh? How do I get something other than a 1 or a 0? Okay, I'm thinking there's something to do with the GCD here. Yeah, okay. Interesting. That was kind of what I was thinking. In these cases, it looks like the GCD is exactly what you return, but I think it's more than just the GCD, because here you have the GCD is 1. I think it's the sum mod the GCD. I think that's what it is. Maybe I'm wrong, but that's kind of. Are you ready for this? I'll call it A. Is accumulate. Let's call it V. And B I don't know if I can do that. Let me see. I have to look at the. You have to look at the. Excuse me. The function signature. Binary operation. How can I use as a functor? I know I could wrap it in a lambda expression, but I think there's a more appropriate way to do it. Yeah, I want to make it a function object. A lot of this got removed. Okay. Can I just use function? Let's try that. Standard function. It's int. Can I do that? Try that. See if that works, I wonder. Really? Oh, it's templated. That might be why. That could be it. Maybe that's why. Also, my neck. Oh, it works. Hey, look at that. I mean, it doesn't give you the right answer, but what if I did this? Do I even need the other part? Oh, it works. Hey, cool. Okay, that's what I was going for. Yeah, that's what I wanted. I want to use a fold expression, left to right fold expression on the GCD. Cool. And now this is going to be the sum mod b. That's what I suspect is the answer. I don't know if that's correct or true, but it seems to be. No. Output 0, expected 10. No. Maybe this is it. I don't know. It's something like this. Seven. Okay, B should be 10. The GCD is 10. The sum is the other way around. It's the other way around. I don't know. There's something weird going on here. Something strange for sure. These cases, it's just the GCD directly, but here, if I add 1 to the GCD, take the sum, modulo GCD, what do you end up with? A mod B. What does this give you? There's something going on here. There's something, like the GCD seems to be right in a lot of cases. Why would it be different in this case? A mod B is 0. Is it always 0, A mod B? A mod B should always be 0, right? Yeah, A mod B is always 0 because the greatest common divisor divides all the elements, and the sum is the sum of all the elements, which means the sum is divisible by the greatest common divisor, which means it'll be A mod B is 0. Okay. So then why do I end up with the GCD in these cases? And is it always the case that I get the GCD in some of these cases? Here we got GCD is 1, but when I added 1, instead of getting 1, I got 0. Huh. How is this related to the GCD? And this would go back to, if I add another one. I don't quite see it. There's some kind of relationship here. It's not obvious. I don't really have a proof for it. So it goes, when you add another one, it goes back to the GCD again of 1. Try something less, a little more involved. Let's add 60 a few times. Okay. Add 60 a few times, it's still just this GCD. Looks like it doesn't matter how many times I add 60 in there. Adding 10 a few times changes things. Just noticing some things here. Maybe there's some pattern here that I can use. So this goes to 0 when I add another 10. Adding another 10 puts me at 10 again. Okay. How about adding a 20? Does that change things? Curious. I think it doesn't change anything. Yeah, it's still GCD is 10. It looks like it's the GCD, and then if you have multiple instances of the GCD, they affect each other, and they toggle between 0 and 10. So basically, if you have an even number of GCD values, even frequency. I don't think it's actually the sum that matters. I think it's the call it D. And we're gonna say now hold on. Let's get something that has a different GCD. Let's go back. Let's have something that has a GCD that's not equal to the smaller value. So here the GCD is 2. This is more interesting. Let's try this one. More interesting case is when the GCD is not exactly the smallest element. Okay, so it's 2. All right. What happens if I add another value? Let's say another 4, or even let's do 10. Let's do 8. Let's do 10. Let's do 4. How do those things change? How do those things change the result? So number 6. So here it's 2. Adding another value 8 doesn't seem to matter much. Still 2. Adding 10. Oh, okay. End up with 0 now. All right. That's different. So maybe the sum does matter. Okay. Then 8, 4, 6, and 4 end up with 2 again. Okay. Interesting. Here, the sum is 20. GCD is 2. Expected is 0. Here the sum is 8, 14. GCD is 2. You get 2. Okay. I don't think it's as obviously related to the GCD as I thought. I think it might have some kind of relationship to the GCD at some points, but I don't think it's as clear of a relationship as I would like it to be. Okay. I'd say 10 and 4, I get 6. If I take 6 and 4, I get 2. 10 and 2 is 8. Is that right? So if I do 6 and 4, I get 2. I do 10 and 2, I get 8. So I could get 8. So I think if you can destroy these, then you should. Maybe that's part of this too. So this is not obvious how to approach this. I'm not really sure. I'm looking for some kind of a shortcut to do this efficiently, because I don't think you can do this too easily, like with a brute force approach. So 10 minus 6 gives you 4. So all the pairs that are possible initially, it's 4 and 6 or 4 and 10. 4 and 6 leaves me with a 2, and 4 and 10 leaves me with a 6. 6 and 6 gives me 0. 2 and 10 leaves me with an 8. Leaves me with an 8. So it's possible to get 8, but it looks like if it's possible to destroy all the stones, then I should return 0. Okay. All right. Yeah, there's like repeated differences going on here. I think that's why I'm thinking about the GCD, why it seems to like it might matter. Excuse me. Oh, the other selection I could make is 4 and 6, 4 and 10. I could also make 6 and 10 and get 4 and 4. I think do I always want to get maybe I can select pairs efficiently. So I think the pairs that are closest to each other are 6 and 4. And then I end up with 2 and 10, which gives me a difference of 8. So it's sort of a load balancing thing where I don't necessarily take the closest elements. It looks like 6 and 10. These are further away from each other. You get a 4, but it gives you 0 at the end. It's also how I should understand this. If I can get 0, then I should get 0. It kind of seems like as long as you don't get 0, you're always going to get the GCD. That's sort of the impression I get here. The GCD unless it's 0. And when is it 0 is the question. Try some random things here. And then try some things that have a GCD of 3. Very interesting question. I don't know. Don't think I really need these two. Yeah, it's almost always the GCD, except sometimes it's not. Oh, expected 12. Okay. 12. Whoa. That's different. Let me see. 12, really? Oh, okay. So here's an idea. If you have one very large stone, okay. I think if you have one very large stone, you remove all the other stones from it, then that's as small as it can get, right? Because I think you just always take the largest stone and subtract the next largest from it. I think that's it. I think you do this with just a set, do an n log n time. And the reason is that if you have a stone that's larger than everything else combined, then you want to subtract as much from that as you can. And if you subtract anything if you select any other pair, you won't get the maximum you're looking for. So if you have a stone that's larger than everything else, sum together, and then you always pick that stone. But then why wouldn't you just always pick the largest stone, period? Because once you pick the largest stone and you bring it down in value, then as much as you can, I think, excuse me, then you get another larger stone, and that should be brought down in value, and so on. I'm wondering, excuse me, if I should be bringing the largest stones down in value or bringing the smallest stones down in value. Well, you want the smallest stone left over, right? So you want to keep that around the smaller stones as much as possible. So that way what's left over is a smaller stone. I think that's the impetus for this. So if you go with that algorithm, right, you get 99 minus 36 will give me 63, minus 39 will give me 63 minus 39 will give me 33 minus 9 is 24, 24 minus 21 will give me 3, 3 minus 3 is 0. Is that right? Hold on, let me do that by hand. Let me do it by hand. So yeah, this is a challenging question. It's not obvious at all how to approach this. Just kind of guessing at what might work. Like I said, a kind of a greedy approach. Because a brute force approach, I think, would some kind of brute force approach, I think, would be too time consuming. So I got to find some kind of way to do this. Oh, okay, so now 24. All right, so we take 99 minus 39, and you get 60. 60 minus 36 gives me 24. Then it's going to be 30 minus 24 gives me 6. And then 21 minus 6 is 15, and then 15 minus 3 is 12. Yeah, I think that's the way to go. I think that's the way to go. You just take the top two elements each time. So you can create a heap. You begin, the end, and this is going to be not a min heap, but a max heap. So is greater than. And then we're going to say while v is not empty. Pop heap, we're going to say a is v0. excuse me, v size is greater than 2. Or is greater than 1. A is v0. B is, and we're going to pop it. B is v1, the next largest value. Now we're going to say the difference is largest minus next largest. And we're actually going to pop both, believe it or not, and then push diff into the heap, which the signature may not be totally correct. Yeah. You got to push onto the back first, and then push that into the heap. Pop push, and that's while it's greater than 1 element left. We say if, so return B is empty, return 0, otherwise return B is 0. I don't know if this ternary expression will work properly, by the way. It might give me a runtime error. Could be wrong about that. I just have to use a branch statement if statement. What? Oh, I didn't see that. Typo. I forgot, don't have to give that third parameter because you automatically, have to push it on the back anyway. Oh, almost. Should have gotten 12 for this though. I did something wrong, I'm sure. I don't really use these functions often enough to kind of know it all offhand. Maybe it is supposed to be a min heap or a max heap or something. The one that's incorrect. Oh, look at that. What happened there? What? 3 and 30. Excuse me. Wait, what? Huh? I think it's supposed to be the other way around. I think it creates a max heap when you use the min. Something like that. It's confusing, but... Oh, this is supposed to be v0. That might be why. Yeah, okay. That's part of it. Yeah, so I turned it into the wrong kind of heap. I didn't need to do all that. That's confusing. It's a Yeah, there we go. Okay, that's what it's supposed to be. It looks like my ternary expression is okay. Okay, that's fine. All right. It's a max heap by default. It uses a less than comparator to give you a max heap, which is a little confusing, but that's okay. Because you'd kind of expect that the less than operator would give you a min heap, as in the element at the top is less than everything else, but it's actually the way around. Using a less than comparator makes the element at the top be a max heap, which is kind of what I got confused about. I think this is the answer. I think this is it. I think it's that simple. This is n log n time, I think. So I'm pushing. Oh, not the answer. Wrong. Okay. Well, incorrect. All right. So I'm wrong. I'm wrong. Kind of just guessing for the most part. Works in some cases, but in this case it's incorrect. (21, 26, 31, 33, 40). Okay. Output should be, my output was 9, it should be 5. So I said take 40 and 21, and we get 19. And then take 33 and 26, we get 5. 5, 19, 31. 31 and 19, get 12, 5. And 12 and 5, we get 7. How did I get 9? Well, wait, why did I? What? 21, 26, 31, 33, 40. Okay. So I take 40 and 30. Now we get 7. Oh, that's what I did wrong. Okay. So 7, 21, 26, 31. Then I would take 26 and 31, get 5, get 5, 7, 21. And I'll get 21 and 7, get 14. 5 and 14 gives me 9. Okay, a different approach would give me 5. Let's see if I can go up from 5. 5. Things that have a difference of 5 could be, I don't know, some stone that's left there, which could be, it's 21, 26, 33, 31, 33, 40. So it could be 21 and 26. It could be 26 and 31. It could be 31 and 36. It could be 33 and 38. And it could be 40 and 45. Well, it's not possible to get 45, so it can't be that last one. But starting from 5, those are some of the possibilities. Okay. And now the question is, there's got to be something else, some other state where I can end up at 21, 26, for example. Excuse me. other states that I could end up at 21, 26. Or actually with 5 also you could have, well, you have to get 5 somewhere, somehow. Yeah. So 21 and 26 are differences between other things, other stones. This is actually incorrect, what I just assessed, actually. No, this is wrong. Because 5 could be actually the difference between two other states, x and alpha and beta, we'll call them. And each of those alpha and betas could also themselves be, we'll call it alpha 0 and alpha 1 and beta 0 and beta 1. Let's actually do it the way alpha 0, beta 0, alpha 1, alpha 2, beta 1, beta 2. Like those themselves could have been differences also. Yeah, which makes things more complicated, right? Let's see. I gotta get down to 5. Well, like I said before, I can go through all the possible states. So we have 21 could be paired with 1, 2, 3 other 4 things. So you get 5, 31, 33, 40. It could be 10, 26, 33, 40. It could be 12, 26, 31, 40. It could be 19, 26, 31, 33. And then those have some possibilities. Then you could also do 26. So 21, 26 and 31 is 5. 21, 33, 40. 26 and 33 is 7. 7, 21, 31, 40. And 26 and 40 could be, is that 14? 14, 21, 31, 33. Yeah, 3 possibilities there. And then 31, you could do 31 and 33 is 2, 21, 26, 40. And then 31 and 40 is 9, 21, 26, 31. Or excuse me, 7, 33, and no, yeah, that's right. No, 31 and 9, 40s. Yeah, it's 9, 21, 26, and 33. Yeah, and then finally the last thing we do is 7, 21, 26, and 31. Okay. So there are those possibilities as well. So, okay, any of these cases, these are all the possible 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are basically n choose 2 possibilities. And then there's another n choose 2. I mean, there's like, it's like n choose 2 raised to the n, basically. N choose 2 times n choose, n minus 1 choose 2 times n minus 1, n minus 2 choose 2, dot, dot, dot. That's a lot of, it's a lot of possibilities, let's say. But anyway, to go through. Some of them, maybe I could memorize these states, sort them and memorize them. Technically I could do that. But I think that still would be kind of expensive in terms of time. So one of these gives me a 5 afterwards. Which one could it be? I don't know. Excuse me. Gee. Oh, got it. 9, 21, 26, 33. I can go to 21 and 9 puts me at 12, 26 and 33. 26 and 33 puts me at 12 and 7. 7 minus 12 gives me 5. Got it. Nailed it. Nailed it. Okay. I think if I want to do this effectively, I think I should actually do, I think I need to take advantage. I think maybe I should use a binary search for this. I think this is kind of hard to do like in a more direct way. I think I want a binary search on the possible difference sizes, which is obviously bounded by 100. Okay. So let's try it that way. Let's say, is it possible to get a particular number? I think it's got to be the maximum. Let's start with 40. Is it possible to get a 40? No. Actually, it's the maximum minus the minimum is the largest possible. 40 minus 21 is 19. Yeah, because any other difference is going to be smaller, right? The smallest possible difference, largest possible difference, so it's going to be that difference. Yeah, smallest possible differences between differences. Gee. I mean, it's just the smallest possible difference in general. Yeah, smallest possible difference in general. But also, no, because I've got to get rid of all the stones, so it's not quite that simple. But anyway, it's going to be bounded by 19. So I could try 19, see, can I get 19? Is that possible? Well, if 19 is left over, then there's two numbers, as we mentioned, some alpha 0 and alpha 1, such that alpha 1 is equal to alpha 0 plus 19. I'm looking for this alpha 0 and alpha 0 plus 19. What could alpha be? Yeah, I'm not really sure how to go backwards. I don't know about that. I don't know if there's a particular difference amount, if there's a way for me to get that directly. It doesn't seem obvious at all. No, I don't know about that. So obviously the brute force approach is going to take too much time. While it can work in some small cases, it's just too much. Maybe I just have to pick the option that gives me the minimum difference among all, the smallest maximum difference among all the values. Maybe that's what I need. That seems like a logical thing that might work here. So the largest difference we have 40 and 5 is 35. For each of these, and choose two options when I have 5 elements walking through them. I get the largest differences. Okay. I don't know if that matters. Give me one moment. Just a moment. Okay, excuse me. Sorry about that. That was an important phone call. Yeah, I guess the full disclosure, I had gotten into a pretty bad argument with one of my family members, and I love my family members. I don't really want to have animosity between myself and my family members. That's like the last thing that I want. And I didn't know what to do. I felt pretty bad, but my family member gave me a call, and so we were able to kind of make amends and straighten that out, and that was really good. That was really good. I wasn't sure what we were going to do, what was going to happen, but I've said before in the past that, and I still feel this way, that having bad arguments with family members is not a reason to ditch your family members, right? Like, you could still have a relationship with somebody even though you get into a bad argument. It's just you both have to find a way to make amends, and I'm, generally speaking, I try to be as amicable as I can. Some things are really hard. Sometimes it's really difficult. I struggle a lot sometimes with relationships. It depends on the context, the situation. But generally speaking, you definitely would prefer to be on good terms with other people as much as you can. Pretty much always. It's like almost always better to be on good terms. It does depend on who you're dealing with, though. Some people, and this is getting into more really deep territory. Almost all people you want to be on good terms with them, but there are some people that, um, basically, they themselves never actually want to be on good terms with you, and it's pretty complicated how to recognize who those people are and why, but has to do with actually has to do with genetics of all things. So it's very. I could start talking about it, but it's even talking about it's kind of hard. so I'll go into that here. It's like a different kind of subject for another time. But just about everybody, aside from a very small number of people, would be, well, not a small number of people, I should say. Well, it gets complicated, but I would say for sure with my family members, they definitely are in the category of people I pretty much always want to be on good terms with. Yeah, and I'm like pretty disappointed. I've talked about this in the past. One of my family members doesn't want to speak to me, and I don't really understand it. And I think I may have offended him in the past, and maybe I should try to apologize to him, but I don't really know how or when or what to do. And I've said kind of nasty things about him in the past too. Oh, stream is dropping. Hold on a second. We wait the stream to come back. Yeah, my internet connection is very spotty. I hadn't really dropped frames all day for like an hour or so. Oh, here we go. We're back. Yeah, I hadn't dropped frames for a while, and all of a sudden it dropped frames. Excuse me. Anyway, yeah. So I pretty much always want to be on good terms with my family members, and so that was really good. And I definitely want to pick up that phone call. And then I have another family member that has kind of been estranged for a while now, and I don't really know what to do about it. But I realized probably whatever I did was probably not good. Like, to get into an argument with this other different family member, and yeah, he actually wanted to get some space from me, away from me for a while, which is like, okay, I guess. Like, what else am I gonna do? What else am I gonna say? But I didn't really understand that at the time. I don't really understand that now. I'm still kind of struggling with that, I guess. But I don't know. I think I'll figure it out. I think it's important for me to recognize that I need to kind of give some ground where it's needed to make peace, sort of make peace with my family members when needed to do so. And I should definitely try to be sort of on their team, on their side, and vice versa. Try to have them on my team, on my side. We should be unified as much as possible. It's very important, very significant. And I love my family members. Like, I don't know. It's one of those things that's worth saying. Even if sometimes they could be difficult, or it's not even so much that they're difficult. Like, I realize that I am not perfect. Like, I do things that are not good from time to time, and not good. Like, that are difficult, things that are difficult for my family members to deal with, and I recognize that too. That's really important. Um, and I'm kind of learning more about that and kind of working through that as well. Because I noticed that when I have really bad interactions with my family members, it seems to be that I could have done things differently, and I should have actually. I should be better. Like I should be a better person, stronger, more disciplined, more self-control, more aware, like less on my end, like less emotional in my thinking, or actually even better than that, like more aware of how emotions play into things, how important emotions are. That seems to be like the biggest problem, I think, not just with me and my personal life, but like the culture at large, like the whole country. All of our sort of all of my people, so to speak, not just my immediate family, but like my ethnic kin and brethren and sisters and all of that. Um, all of us, I think, really struggle with emotional kind of thinking, and not also not thinking when we're trying to think about things rationally, not thinking about how emotions play into things. Um, yeah, yeah, and anyway, yeah. So I don't know. I kind of rambling now, but I've been doing a lot of thinking about like myself and how I deal with other people, and especially friends and family, people who are close to me. And it struck me that like, yes, my friends and family are not perfect for sure, but certainly I am not perfect, right? Like there's like a lot of room for improvement on my end, from sort of how I tend to interact with with others. Uh, and a lot of that has to do with just being mindful of how emotions come into play. Like if somebody's really frustrated, probably should let them calm down a little bit before you know, either whatever you might want to interact with them over. Like either confront them once, like definitely not a good time to confront somebody is when they're frustrated, right? Right. You're gonna challenge them on something, like it's not a good time to do it, and so on. There's all kinds of things that are, I mean, that seems like really obvious, but it's actually like very, very significant. Like emotions are very, very powerful things. And also this idea that like people tend to be more emotional than rational anyway. In terms of how they make decisions, when they make decisions, they tend to be very emotional. Um, and that seems to be like how they do things, how things happen. And yeah, and like sometimes you just gotta let people kind of come to their senses, I guess. Um, a little bit, depending on what the circumstances are, I guess. Um, yeah, but yeah, that seems to be the thing for me. Like I really struggle to pay attention, like give enough, like pay enough attention. I don't pay enough attention generally to how important emotions are. How important they are. Like if someone's really frustrated, uh kind of not engaging them as much until they've kind of gotten to a more relaxed state. Um, and I have a very hard time like paying attention to like other people's emotions, I think. I don't know. I just never thought of that. Like, it's never thought to like. I kind of have to like train myself a little bit to like pay attention. Like, pay attention when people are emotional. Like, pay attention. You know. And yeah, that's on my end. That's for sure. That's a big thing. And also like when I'm trying to talk to somebody about something, like maybe I want to convince them of something, like it's more effective, and it's actually probably more likely too that the reason they don't see things the way you see it is not for logical reasons but for emotional reasons, right? I think a lot of disagreements tend to be emotional disagreements more so than rational disagreements. um, like someone holds a position because of emotional reasons. Okay. Is it working? Gee, oh boy. This is like 5 minutes it's been going for. It's just drop frames like crazy. Okay, let's go now. Alright, I think we're back. That was like a solid 5 minutes, or it was just But anyway, yeah, what I was saying was important, that people tend to hold positions that they hold for emotional reasons, not for logical reasons. Um, and it's very easy to get into an extremely irrational exchange with somebody when emotions are flaring up. So it's very important to think about emotions, consider them. Anyway, so yeah, I want to get back to this question. So yeah, one of the things I struggle with, obviously, is that my internet connection can be very spotty. And I don't know, I'll just kind of have to figure that out as I go. Figure that out as I go. One of the things I wanted to return to. So anyway, yeah. So that was really good. That was a good phone call to take, and I'm grateful. And yeah, and I don't know. It gives me some hope also that I might be able to make amends with my other family member who's been estranged, which it's not good for me to be at odds with my other family member as well, even though, I've done things to him that I shouldn't have done, and he's done things to me that he shouldn't have done, and like we could probably like meet there. And I could apologize to him, and he could apologize to me, and like that could be fine. That could be fine, because it's almost always you want to be in good standing with your family members. Almost always. Very rarely does it. Oh, I would say pretty much never. Pretty much never is it good to be at odds with your own family. So okay, so this question's a tough one. I don't know the answer. Still working on it, working through it, trying to figure out. Still working through it, trying to figure out what to make of it, to do with it here. And what do I need? So okay, yeah, very long time I've spent on this question now. It's been quite a bit time chatting, and also spent quite a bit of time chatting, and also quite a bit of time chatting, and also yeah, I don't really have an answer to this. I mean, I have the brute force approach, where you could pick any particular pair and then try to get the optimal solution based off of those pairs, and so on. But that would be a very expensive algorithm in terms of time. So there's got to be some way to make this a little bit easier. Maybe again, a similar, with the stones. These stones questions are like, they're always so difficult. Maybe using some kind of sliding window again. Possibly, I don't know. And maybe some kind of binary search might work. Maybe some kind of dynamic programming solution might work. I don't really know. Yeah, I don't know. How could I think about this? I mean, maybe I'm thinking a sliding window is probably the way to go. It's got to be. It's either that or a dynamic programming solution, or I don't see an obvious binary search solution. That seems kind of hard to see if it exists. No, I don't think so. Excuse me. If I look at the difference array, I see 5 all over the place here. From left to right, I see 5, 5, 12, 7, 7. And then the difference array there is 0, 7, and 5. Look at that. And that one is 7, 2, and this one's 5. Maybe I just take a sequences of difference arrays. I mean, I could do it that way. That seems kind of bad, but does that work? Is that it? That would be kind of simple, kind of easy. Okay, let's try it with another example. 2, 7, 4, 1, 8, 1. Differences are 5. 3, 3, 7, and 7. Differences there are 2, 0, 4, 0, 2, 4, 4, 2, 0, 2. 1. Oh. Okay. Let me sort it first. What is that sound? Oh my goodness. 1, 1, 2, 4, 7, 8. Okay, let's try that. 0, 1, 2, 3, 1. And then maybe sort these too. Maybe do I have to sort them both? I don't know. Maybe not. I don't know if I need to. 1, 1, 1, 2, 0, 0, 1, 0, 1, 1. Do I just need to sort it and then just take all of the differences over and over until I'm down all the way to the bottom? Is that it? Seems like some kind of dynamic programming solution, but if I do it this way, it'll give me the same answer. That's kind of weird. It's weird that seems to work. I don't know why that would work, but apparently it does. Of course it does. No idea why. 23, 31, 46, 50, 70, and 100. Okay. Differences here we get 8, 15, 4, 10, 30. Differences there, 7, 11, 6, 20. Differences there, 4, 5, 14, 1, and 9, and 8. Expected 12. I got 8. All right. 23, 31, 46, 50, 70, 100. That's a difference of 8, 15, 4. Oh, it's 20, not 10. Oh, that might be why. 30. We get 7, 11, 16, and 10. Then we get 4. Oh, still get 5 anyway. 5 and 6. 5 and 4 is 1. 6 and 5 is 1. 0. I got 0 for that one. All right. Well, it doesn't work in that case. Okay. 2, 4, 5, 6, 10, 10, 30, 23, 30, 34. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. Okay. 2, 1, 1, 4, 0, 13, 7. No. 4, 11. 11. This becomes 1, 0, 3, 4, 13, 2, 1, 3, 1, 9, 11, 2, 2, 8, 3, 2. That's 2. 0, 6, 6 and 606. Okay. That one's 0. All right, so this idea is just doesn't actually work. Seems like it might be relevant at some points, but it's not correct. But it's an interesting idea. Hmm. Well, I mean, that first row of differences are all the possible. Well, no, those are the smallest possible differences, right? Those are all the smallest possible differences, and then there could be more differences among them that might be helpful. I'm not too sure about this. Yeah, this is definitely getting into that kind of territory of like some kind of sliding window or some kind of DP or something unusual kind of required, not so obvious. Something that is not very obvious how to do this. Maybe some sorting involved, maybe not, I don't know. Maybe a heap of some sort. I don't know. Well, I don't know. Let's look at 23, 31, 46, 50, 70, and 100. Okay. If I take some random pair, I could say 50 and 31. Let's say I have my range from 23 to 100, right? That's the range of numbers I'm looking at. 50 minus 31 gives me 4, 1, 9, 1, 19. Now we have 19, 23, 46, 70 to 100. Now the range is from 19 to 100. The range got larger. What if I could make the range smaller, either on the left side or the right side? So on the right side, I could take 100. Like that's kind of what I was thinking. I could always make the range smaller on the right side. 23, 31, 46, 50, 70. I could use 100 and I could subtract anything that puts me above 23, right? So 100 minus 70 puts me at 30. 100 minus 50 puts me at 50. I probably want to pick the biggest one, quite frankly, because I want to get as far to the left as I can. I do, yeah, so probably should be that one, which was very similar to what I was thinking before. So I did 170. That would put me at 23, 31, 46, 50, and 30, which is just 23, 30, 31, 46, 50. Okay. So maximal change in the size of this interval from the smallest to the largest. That puts me now at 23 and 50. Now I can take 50 and 46, but that would give me 4 and 31, which now this range was 50 minus 23 plus 1, puts me at 30 minus 7, 30 minus 3 plus 1 is 28. And then 31 minus 4 plus 1 is also 28. So actually no improvement if I do it that way, right? Yes, that's interesting. 20, is that right? Yes, 28. Yeah. So I'm thinking maybe what I want to do is I want to make my range of numbers as small as possible. The range of numbers as small as possible, right? I think that's consistent each time. I could maybe a greedy algorithm to do that. Maybe using sliding window to do that too. So yeah, 46 and 50 actually isn't that great. I could do, and if I do anything 50 and something else, like if I do 50 and 30, right? That gives me a 20. That actually increased the left side of the range. So now I'll get 20 and 46. 46 minus 20 plus 1 is 27, which is better than the other one, but still not great. So about 50 and 31, that gives me 19 and 46, which is 28, right? So it's actually not the best. So I think the best improvement initially is going to be 170, but 50 and 46 is not the best. 50 and 46 is okay. That's better than some of the, I don't know. Yeah, 50 and 46 would put me at 4 to 31, which has 28 elements. But also I can do 46 and 50 is one option. 31 and 50 is a worse option in terms of extending the size of the range. 30 and 50 is like comparable to 46 and 50, but what about 23 and something else, right? 23 and 30 maybe. If I did that, that would give me 7, and now we're at 7 to 50. That's not much better. That would be 50 plus 7, 50 minus 7 plus 1, which is 44. That's not very good. How about 23 and 31? That's not much better. That's 8. Still not very good. 23 and 46 is 23 again. That just puts me at 23 and 50 again, which is exactly where I started, which is not an improvement. Which I think is 28, right? 50 minus 23 plus 1 is, yeah, it's 28 again. So no, 23 and 46 isn't very good. So those are really the only options, is to delete 27 and wait, how did I do this? Oh no, wait, hold on. Did I do that right? Well, if I do 50 and 23, hold on, what am I doing here? It puts me at 27, right? And then I have 27, 30, 31, and 46. 46 minus 27 is 19. That's the best, actually. That's the optimal one. Not sure how exactly I can figure out which one's optimal quickly, but I think I can. I think it's possible. But I think that's what I want to go for. So that's 23, 31, 46, 50, 70, and 100. Initially, it's 100 minus 23 is 78 elements, right? And then somehow I can determine going down to 23, 30, 31, 46, 50, which gives me 23 to 50 is 28 elements, right? That's the most I can remove, and then I think the next move, the most I can remove, I can go down to 27, 30, 31, 46, and that puts me at 27 to 46, which I think is actually quite a lot, or no, it's quite a difference. I don't know, 19 elements? It's 20 elements. No, it's 19. Yeah, 20 elements. So I can go down to 20 elements now, which I think is the best I could do there. Again, I'm not really proving that these are the best, but there's probably a way to prove it. This might give me a cubic time algorithm if I do it this way. I could definitely try every possibility at each step, and there's only n steps. That would give me cubic time. But then, what are my next options to make this range as small as possible? 46 and 27. Excuse me, 3, 1, 9, 19 again. Yeah, and then I would be at 19, 30, and 31. 31 minus 19 is 2, 2, 1, 12. 12, 13. 19 to 31 will put me at 13 elements in the range. But I think the other options would be 46 and 31, which is 15. 15 to 31, which is more elements. It's 4 more elements. 46 minus 30 would be 16. 16 to 31. 16 elements. Yeah. And then 31 and 27 would put me at 4, 30, 31, 30, 46, which is, if you just modify the things in the middle, I don't think it doesn't improve anything. So it has to be either the left side or the right side. So actually that could be a linear pass. Then this would be quadratic if I did it that way. Because yeah, if you only do the things on the inside, then those will only ever either increase the boundaries that I had, or just shift the elements around internally, which just keeps the same boundaries again. Assuming that's what I need to do, is to move things closer. Yeah, so those are really the only options. So in which case you would want to do 27 and 31, I think, which gives me a 430. Yeah, it gives me 4 to 46, which is 46 minus 4 plus 1 is 43, and that's definitely way more than what I had at this point. In fact, I think this actually could be done in constant and linear time again, if this is the correct approach, because aside from taking the minimum and the maximum values, there's maybe not, well, I don't know. Let's just say it could be done relatively quickly. Then there's 46 and 30 and 27 and 31, and as I move closer to 27, combining 27 with another value, that's just going to get smaller towards the left. That's just going to increase the interval size on the left side. And then same thing in the other direction, from 46 and 27, anything larger than 27, that's going to, or excuse me, 46 and 31, that's going to give the largest element on the left side. And then as I go down, same thing, it's just going to move further to the left. It's not obvious exactly how to pick those things, though. I don't know, maybe it's not. quadratic or linear. Maybe I don't know. Maybe I do need to go through all the possibilities there. I got to think about that a little bit more. But even if I did all the possibilities, it would still be efficient enough for these test cases. But I think here in this case, it's 46 and 27 is what I want to use. That puts me at 19. That goes 19 to 31. Yeah, the other options are, which is 13 elements. The other options are not as great. So let's do that. And then again, we could do 31 and 19. 12 and 30. That was 19 elements. And then yeah, so I could do 19 and 31. I could do 19 and 30. If I did 30 minus 19, that's 11 to 31, which I think is also 19 elements. No. That's 21 elements. Not as good. Oh, yeah, right. So, wait. 12 to 30 is 19 elements. Yeah, that's right. 21 elements. Okay, it's a little confusing, but yes. And then finally, you can do 30 and 31, which is gives you a 1, and you have 1 to 19. 19 minus 1 plus 1 is 19. Yeah, so the optimal, the best, is well, actually either one works. Yeah, you could do 1 to 19 is 19, and then 12 to 30 is 19. Let's do 1 to 19, and at the end of that you get 18. And I think that's the solution for that 21, 18. Oh, expected 12. Oh, whoa. 23, 31, 46, 7. Oh, okay. It's supposed to be 12. I got 18. Whoops. What? I don't know. What did I do here? Whoops. Let's do 123. Let's try it that way. Let's just do the maximal. Let's try again. Let's try again. That's 77 I get. $31, 46, 50, 70 to 77. What's 77 to 31? That's 46. Okay. And then 77 minus 31, we get 46. Oh, yeah. So 46 twice, 50 to 70. 70 minus 46. So this is first, it's 78 elements. Then it's 47 elements. Then it's 25 elements. We get 24, 46, 50, and 50. Which is 50 minus 24 is 27 elements. Is that right? 27 elements? No, that can't be right. Oh, whoops. 70 minus 46. Wait, what? Uh-oh. Whoops. Huh. Uh-oh. Actually, you could just go 46 and 46 here and get 50 and 70. We get 21 elements. That puts me at 20, which is not what I want. Okay. Whatever I'm doing, I'm not doing it right. Maybe I do need to go through all the possibilities. Get ahead of myself trying to optimize this here. Premature optimizations here. Okay. Let's try again. 23, 31, 46, 50, 70, 100. Okay. How am I doing on time? So yeah, haven't figured out the algorithm yet. Something that works. Figured out an algorithm, but yeah, here 100 minus 23 is 77. So this is 78 elements in this range. Now the possible pairs, PP, possible pairs: 123, 131, 146, 150, 170. 70 and 23, 70 and 31, 70, 46, 70 and 31. Already did 70 and 23. Oh no, 70 and 23 as well. Oh no, we did 73 already. 23, 31, 46, 50 it should be. 50 and 23, 50 and 40, 31, 50 and 46. 46 and 23, 46 and 31. And then finally 31, 23. Okay. Okay, so if I were to take each of those combinations, right, those are all the possibilities. I think the minimum I just want the smallest interval range at the end of it. That's what I want. So 123, we get 77, did that before. 131 is 69, I think. 146 gives me 54. 150 gives me 50. 170 gives me 30. 70 and 23 is 47. 70 and 31, 39. 70 and 46 is 24. 70 and 50 is 20. 50 and 23 is 27. 50 and 31 is 19. 50 and 4 is 4. 46 and 23 is 23. And 46 and 31 is 15. Okay. So now the interval ranges that these end up with. It's like 15 different options here. It's kind of a lot. 7 choose 2? No, it's 6 choose 2. 6 times 5 over 2. Yeah, it's 15. Okay. Now, the ranges I get for these 15 options, it's 77 minus 20, 77, 23 to 77, which we said before. It's 55, or it's 55 numbers. 2, when you do 31 and 100, you get still 23 to 77, which is 55. 3, 146 gives me a 54. So that's still the same range. Um, a 100 and 50 puts me at 50. It's still 23 to 70. Oh, excuse me, these are 70, not 77. Oh, no. Actually, these other ones are improved slightly, not 55. Whoops. Did these things incorrectly. 70 minus 23 is 47. So that's 48, and that's 48, and that's 48. And the fifth one, 170, we actually get 30. 23 now to 50, because 70 was used. And 50 minus 23 is 27. Okay, that's probably the best one out of those, is the 23 to 50. Interesting. Okay, then we've got 70 and 23, we get 31 to 100, I think. Yeah, 70 minus 23 is 47. Yeah, that's 131 is I think 69, 70 elements. Oh, I did that wrong too. 50 minus 23 is 27, but this should be 28 elements. 70 minus 23, yeah, okay. Making mistakes here. It's okay, but 70 and 31, I think, is 39? Yeah, that's 23 to 100, which is the largest range so far. 100 minus 23, 78 elements. 46 and 70 is 24? 23 to 100 still? Okay. I'm not sure. I have to think about this a little bit more, I'm sure. But yeah, the raw computation here is like, it's kind of rough, I have to say. It's kind of involved. It's a lot of just calculating. Maybe I could have picked a smaller test case. I probably should have. Probably should have picked up a smaller test case to do by hand here. 70 and 50 is 20. And that puts you actually at 20 to 100, which is actually the largest one seen so far, 81. And then the next one was I'm missing something on top of it. I432. Oh yeah. This actually should be 10, 11, 12, 13, 14. 15 is 31 and 23. I missed that before. Should be 8. Oh. It's freaking. I probably shouldn't make that noise too frequently. Probably shouldn't make that noise. It's not a very masculine noise to make. Yeah, grunting. Okay. Yeah, I don't know. Okay, all right. 15, 23 is 27. And we end up with 23 to 100 again, which is still 78. 11 is 15, 31 is 19. So we have 19 to 100, which is even more. 100 minus 19. 81. And then finally there's a 4 in there, 4 to 100. Not finally, but next. 97. Then 13, we get 23. Okay, 23 to 100, which we said I think was 78. 14, we get 46 to 31. It's 15 to 100, which is 85, 86 elements. And the last one, 8 to 100, is 93 elements. Okay. So the best one to pick seems to be option 5 with 28 elements in the interval, putting me at 23 to 50, and that's 170. So yeah, 23, 30, 31, 46, and 50. That seems to be the best. Now I could pick 50 and 46, or 23 and 30, or 23 and 50. I think those are like the 3 main options that are really relevant. But this is 5 choose 2 now, which is which is 10 options to pick from now. Oh boy, 10 things to work through by hand now. Probably just show what I'm working on. Well, let's just go through those options. So 30 minus 23 is 7 to 50, which 50 minus 7 is 43. It gives me 44 elements. 46 and 50 puts me at 4 to 31, which is 28 elements total, which is not too bad. And then lastly, we have 50 minus 23, which gives me 27, and it puts me at 23 to 46, which is, I think, 24 total elements. It's probably the best one. Now we can go to 23, 27, 30, 31, 46. Okay. Next options are, again, 23 and 27, 31 and 46, or 23 and 46. Okay, 27 and 23 will put me at 4 to 46, which is 43 elements. 31 and 46 would put me at 15 to 30. Yeah, 15 to 30, which is, I think, 16 elements. And the last option, 46 and 23, would put me at 23 and 31, which I think is 9 elements. 31 minus 23 is 9 elements. Yeah, that's the best one. So now we go 23, 27, 30, and 31. Again, next options are 23 and 31, 23 and 27, 30 and 31. If I pick 27 and 23, I get 4. That gives me from 4 to 31. That gives me way more elements. 31 minus 4 is 31 minus 4 is 28. 27 plus 1 is 28. Yeah. On the other side, 30 and 31 gives me 1 to 27, which is 28 again. And the last option is 31 and 23, which gives me an 8. And that puts me at 8 to 30, which gives me 23. So any of these choices will actually increase the range now to 23. So maybe this idea is not quite what I want. Maybe not. So yeah, that's the last one I pick. It's going to be 8, 7, and 30. Of course. And then now I can take 30 and 27. So now the options are, how did I get 18 for this one? This is not true. Or 12. How did I get 12? 12? How did I get 12? I got a number here that's like 5. What? What is going on? What is happening? Oh no. Oh, I gotta be kidding me. What? Well, anyway, the options again. 3 different options. 30 and 8 puts me at 22 and 27, which there are 6 elements there. 27 and 8 puts me at 19 to 30, which is I think 12 elements. 30 minus 19 is 11. 12 elements total. And then I get 22 and 27. What did I just, what? Oh yeah. 8 and 30 or 8 and 27 puts me at 19 and 30, or 27 and 30 puts me at 3 and 8, which is 6 elements. And both of those would give me a 22 and 27 are the only things left. That puts me at 5, and 8 and 3 puts me at 5, and then 19 and 30 puts me at 12. I can get 5, but they're saying it's 12. I think they're wrong. Oh no. Uh-oh. Excuse me. What if they're wrong? Uh-oh. One more time. 23, 31, 23, 31, 46, 50, 70, 100. Pick 170, we get 30. So I get 23, 30, 31, 46, 50. Now pick 23 and 50. I must have done some math wrong. It's got to be. We have 27. Now we have 27, 30, 31, 46. Now pick. Oh, I did that wrong. That's still okay. Yeah, I did that wrong. Okay. Whoops. This whole part's wrong. I picked 23 and 50. 7 to 50. 4 to 31. Oh yeah, I did that wrong. Should have been 27 to 46. Whoops. So I picked 27 to 46. And or 27 minus, yeah, pick. So I get 19, 30, and 31. I picked 27 and 46 for the next pair. And then now the question is, there's a few options. There's 19 and 30 could be one pick. 30 and 31 could be another pick. And then 19 and 31 could be another pick. 30 minus 19 is 11. It's 11 and 31. Then, 30 and 31 and 30 is 1. 1 and 19. And then finally, the last one is, I think, 31 and 19, which is 12. 12 and 30. And all of these are, this one is 20. This one is 18, and this one is 18. Yeah. So you could pick any one of those to get the 18. So I think 31 and 19 is fine. You get 12 to 30, and then you get 18 at the end. Okay. The sizes of these intervals at each step is 100 minus 23 is 7, so 70. Size of the interval is 78. 50 minus 23 is 28. 46 minus 27 is 20. 31 minus 19 is 13. That's not 13. Is that 13? That is 13. Oh, okay. Yeah, so it doesn't always go down the way that I've done this. Trying to get the smallest interval possible, but actually at times it bounces upwards. I don't know what to say about that. So it could be used as like a general heuristic, but not so obvious. So it's interesting that some elements can eliminate themselves entirely as well. That's kind of interesting. Excuse me. I don't know what to think about this algorithm, like what this is actually calculating. Not what it's actually calculating, but some kind of analogy for what this is calculating in order to get a some kind of analogy in order to get a an idea. But this would be basically O of n log n time. Basically to sort the three best options are going to be to take the two largest elements, take the two smallest elements, or take the largest and the smallest. And I could use a set to do this. And yeah, those are the, I think those are the optimal choices that you have to pick from. Don't really have a proof for that. Just seems to be the way to go. That would give me n log n time. Works in some cases. Works in some cases. Excuse me. Yes, it's not clear that this solution would work, this idea. So again, I probably should keep this open. All right. I don't know the answer. Sliding window, maybe, I don't know. Binary search probably doesn't seem likely. What could it be? What could it be? I don't know. I don't know. I don't know. Excuse me. Huh. I don't know, man. I don't know. This is a good question. It's a good one. Definitely a good question. These stone questions are so challenging. Gotta say. Who would have thought stones would be so complicated? They're just rocks. Well, you could ask all kinds of questions about those rocks. Mathematical questions. All right. So I can eliminate two stones and get a smaller stone, right? And if that stone is empty, it's zero. It just disappears altogether. And I'm trying to end up with the smallest amount left over. Okay. Excuse me. You know what? Actually, I'm thinking I could use the property because the stones are limited from 1 to 100. I think I could use that property to solve this in a more efficient time bound than I realize. I think so. I think I could use dynamic programming here and I don't realize it. Maybe? I don't know. Huh. Gee. Well, for sure I can remove any duplicates. Get it down to, and if you have I have an even number of duplicates, I can bring that down to. I could also use counting sort to sort this quickly, but it's only 30 elements, so sorting it's not really that big of a deal. Okay, suppose I didn't have any duplicates. Sure, why not? Not really that big of a deal, but okay. What's weird about this is that if I eliminate one element, right, and I reduce the size of another element, then comparing that element to something else, it now has a smaller size than it had before. Like, yeah, and you can't remove as much now. Almost like I just want to remove as much from the total as possible. It's kind of what I'm thinking. Remove as much from the total as possible. Excuse me. Excuse me. Gotta think about this. So if one of the elements is larger than the sum of all the other elements, then the answer is just going to be that largest element minus all the other elements. Because anything else you do is going to it's going to give you a bigger number at the end. So that's the first thing to consider. Now, what if I'm in a situation where that's not the case, right? So the largest element is not larger than the sum of all the other elements. What about that scenario? Well, that means it would be larger than the sum of a few other elements, but not all of them. Okay. In that case, after I remove some number of other elements, that would no longer be the largest element. Okay. maybe I just at every step want to reduce the size of the largest element as much as possible. That's what I tried before. It didn't work though. In that case, you would always just take the two largest elements and use those. Or I would always do that. Why doesn't that work? It seems like that should work. Also, that ternary operation I had before, I'll end up with a 0 if the way that I coded it before. I'll always end up with an element at the end. So, forgot about that. I'll end up with a 0 at some points. This is very similar to the other stone question, isn't it? Because if I look at the difference between two elements, no, it's similar but different. I was thinking because if I had two stones that were different from each other and I moved one between the two, no, never mind. That doesn't work. Never mind. Just thinking I'd be modifying the difference between them each time if I did that. But here it's the other way around. The difference is the new stone. So in the other case, the new stone is a difference between the previous stones, whereas now, now the new stone is the difference. Yeah. Whereas the other way around, I moved the stone to something between the two. So I added some difference, something like that. That's confusing, but yeah. Different ideas, different things. But yeah, here we're destroying stones and destroying them on each other and making the other ones smaller. This makes for a good puzzle, I have to say. It's a good question. I'm thinking in video games you have different kinds of puzzles. Like a puzzle like this would be a good one. So here's an idea. Maybe I want to have all of the largest elements be as close to each other as possible. So I do want to subtract from the largest element at each step, but I want to take the smallest element away from the largest element at each step. Maybe that's the way to go. If I did it that way, then I would keep updating the largest element, but it would only get slightly smaller each step. And stay relatively close to the other larger elements. I don't have a proof for that, why that would be correct, but it seems intuitively like that would work. Again, I'm pretty sure some kind of greedy approach is the way to go here. I don't think it's a brute force approach is not really going to work. And then there's maybe some optimization you could make somewhere somehow, but it's really not obvious. Really not obvious what it would be. Yeah, so what you do is, excuse me. Okay. I mean, this is probably, it's fine. Okay. 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 Something like this. I could try this one. Try this approach. Oh. Typo. Wrong. Just always wrong. Okay. I tried. And all of these are wrong. No kidding. 21, 26, 33. Excuse me, 20, 21, 26, 31, 33, and 40. 1, 2, 3, 4, 5. All right, so if I did like 100, 1, 2, 3, 4, 5, and 100, pretty sure this last case it works, but all the other cases it's wrong. Oh. What? Huh. Wait, what? could be doing something wrong and not realizing it. Oh, that's why. Duh. I probably shouldn't use v in vowels. That's maybe part of the problem here. Okay, still wrong, but in this case it's at least correct. So yeah, it comes out wrong in this case. 21, 26, 31, 33, and 40. It's almost correct in every spot. It's just, yeah, I don't know. It's kind of tough. Hmm. Hmm. Gee. Well, sometimes it's better to take the. I think the idea that I had before might be correct. I don't know. Where I just, of the three options, I pick the better of the two, or the three. But it might be even easier than that. It might be either it's going to be the. I think I just need to maximize the or minimize the difference between the two largest elements. So initially it would be 30 for this case, or maybe not this one. Let's look at this case, yeah. So initially it's 7, and I could subtract 21 from the largest or 33 from the largest. If I subtract 21 from the largest, then I get 19, 26, 31, 33. And the difference between 31 and 33 is 2. Or I could subtract 33 from the largest, I get 7. And now we have 7, 26, 31. 7, 21, 26, and 31. Now the difference is 5. So if I go 40 and 21, then I get 19, 26, 31, and 33. Now again, my options between 31 and 33 are the largest differences. I can get, actually it's pretty clear to see that I can get 5 now from that. But the next thing would be I can get 2. I get 2, 19, and 26, and that puts me at 7. Or I can get 33 and 19. This gives me 14, 26, and 31. The best difference is 5. Go with that one. And then 14, 26, and 31. I can do 31 and 14. That puts me at 17. 17 and 26. The difference would be from there is 9. Or I can go with the other option, 31 and 26. Which puts me at 5, and now we get 5 and 14. It also gives me 9. Well, actually, both of those are wrong. Both of those are wrong. No. Oh, what if I DP and I go backwards? Aha. It's making me think of the burst balloons question again. I suspect this is I suspect the right answer to this is like these questions are so hard. I suspect the correct answer to this is I suspect that the correct answer to this is oh, deep breath. 21, 26, 31, 33, 40. I suspect the correct answer to this could be 1, a sliding window, or 2, something like a burst balloons type of question. So instead of smashing the stones and having to go through all the different permutations, now I would say, okay, I'm going to pick the last stone to smash, right? So I've got n different options there. And maybe I pick 26 to be the last stone to smash, right? So now I want, there's of the other options, which on the right side, so yeah, maybe this is cubic time solution dp, cubic time dp. On the right side, I've got the sort of the last stone to smash there, and the left side, the last stone to smash. And do I want these to be as small as possible or as large as possible? I want them to be as close to 26 as possible. Maybe it's not a DP, I don't know. Maybe I can adapt this idea. Excuse me. Well, you could mix these up. And the left side and the right side, I mean, they could be, you could move the element or something. 26, 21, 31, 33, 40. Is a subcase, but it's a subcase with different elements. You're actually trying to get the element that's closest to 26 now. So first, you're trying to get the element that's closest to 0. I don't know. That's the, not sure. So of these elements, the final result, we want the element to be as close to 26 as possible. Doesn't really give easy or obvious optimal substructure, quite frankly. Maybe of these ones, 21, 31, 33, and 40. Well, if I add 26 to all the other ones, we get 47, 57, 59, and 66, right? Then I want to find the one that gets closest to 0. So, okay, so of 21, 31, 33, and 40, the sort of f of that sequence, that gives me something as close to 0 as I can get, right? But I actually want something as close to 26 as possible. Closest to 26. So can I just add 26 to everything? No, that doesn't work. Could just add 26 to the result, maybe. Well, gee. I don't know. I don't know about that one. No, it's not so obvious how to do this. I don't know. I don't know the answer. I don't know. This is a tough one, for sure. Differences maybe make has some meaning here. Those are the minimal differences. Oh man, I don't know. Does this give me a 1, 5? What? Yeah, I guess that makes sense. Hmm. Huh. I don't know. Gee. So I kind of wonder if what I ought to do is if it's an odd number of elements versus if it's an even number of elements. If that's kind of relevant here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 8, 6. Go to 5 elements again. So here I can do 1, 1, 2, 4, 7, 8. Yeah, and then I can have 0, 2, and 1. And then we have 2 and 1, and then 1. So this 1, 1. I got a. What are my predictions here? Oh man. expected 1. So yeah, it works if I have an even number, if an odd number of elements. So I think the following sequence works, right? If there's an even number, I take the differences 2 at a time of a sort and take the differences 2 at a time. So I get 0, 2, 1 from 1, 1, 2, 4, 7, 8. 1 and 1 is 0, 2 and 4 is 2, 7, 8 is 1. Now, I recurse on that array of elements, which has an odd number. The first thing I do is I just take the largest element and subtract the smallest element. And now I end up with 2, 1. And then I recurse again. 2, 1 difference is 1. And I get a difference of 1. It works in that case. What about this case? 31, 21, 26, 31, 33, 40. Okay. It's an odd number, so we get 19, 26, 31, 33. And then now I say 7 and 2, and then 7 minus 2 is 5. Done. Next, I go for, which is the right answer, 5. Here we got 23, 31, 46, 50, 70, and 100. 1, 2, 3, 4, 5, 6, right? Okay. Here we get 8, 4, and 30. This is odd, so then I go to 4 and 22, right? 30 minus 8 is 22, and then 4 and 2 is 18. Expected 12. That's wrong. Doesn't work in that case. All right, never mind. Just keep trying different ideas to get something that works. Something that works. You know, I don't know. I don't know. This is a tough question. Sure. Huh. Excuse me. Trying to figure these things out over here. there's just a ton of different possibilities, even for 6. Like 6 choose 2, times 5 choose 2, times 4 choose 2, times 3 choose 2, times 2 choose 2 is 15 times 10 times 6, 4 times 3 times 1, which is a lot. 150 times 9. It's 1,350 possibilities to go through. Which is rather challenging to see that by hand. Which one's the best? Maybe I shouldn't. Maybe these test cases are too large, and I should go through smaller test cases. 5 choose 2 times 4 choose 2 times 3 choose 2. 2 choose 2. 5 times 4 over 2 is 10. Right? 10 times 4 times 3 over 2 is 6, which is 90 possibilities. Maybe even 4 is better to go through. 4, 3, and 2. That's 6 times 3 times 1. It's 18 possibilities. So yeah, I should just have 4 elements at a time. And these 18 possibilities would be 1, 2, 3, 4, 1, 3, 4, 1, 4, 4, 2, 3, 4, 2, 4, 4, 3, 4. 2, 3, 4, 5, 6, and those give me 1, 3, 4, 2, 2, 4, 2, 3, 3, 1, 1, 4, 1, 2, 3, and 1, 1, 2. And each of those have 3 possibilities, which is could be 1, 3, 4. It could be 1, 4, and 3, and then it could be 1, 3, and 4 combined. Each of those gives me 2, 4, which then goes to 2. Then we get 3, 3, which is then 0. And 1, 1, which is then 0. So this can go to 0. 1, 2, 3, 4 should be 0. As soon as you find 0 once, you're done, I think. Let me try some other numbers though. Like what if I did, I think this could all go to 0 too. Let's try some random things. Yeah, some random number. Let's try that one, the second case. So yeah, I got 0. And the 7, 22, 35, 48. A similar kind of a thing. 4 possibilities. Six possibilities rather. So we can get 15, 35, and 48. Get 22, 28, and 48. And we can get 22, 35, and 41. We can get 7, 13, and 48. We can get 7, 26, and 35. Get 7, 22, 13, and 22. Put 35 with 48. 1, 2, 3. Yeah, I've put 35 with 48. Then each of those, we can get 15, 35, and 48 can go to 20 and 48. Can go to 35 and 30, 33 and 35. 20 and 48, 33 and 35, 13 and 15. And then those become each 2, 2, and 28 respectively. Or not respectively, but in some order. Then we got 3 options, 22, 28, and 48. We get 6 and 48. We get 26 and 28. Yeah, 26 and 28, and then we get 20 and 22. Which gives me 42, 2, and 2. Okay. So 2 shows up quite a bit, actually, which is interesting. 35 and 22 becomes 13 and 41. Yeah. And 35 and 41 is 6 and 22. And the other one is 22 and 41, which is 19 and 35, which then each of those become 16? 16, 28, 31 minus 28, 25 minus 9, 16. Yeah, 16 again. Okay, interesting. Okay, next is 6 and 48, which gives me 42, and 48 minus 13 is 35, 7 and 35, which is 28, and yeah, 7 and 35, and then 13 and 41, which is then 28 again. Okay. 7 and 26 puts me at 19 and 35. 7 and 35 puts me at 26 and 28. And then 26 and 35, the difference is 9, so we get 7 and 9. And we get 16, 2, and 2. Okay, and the last thing, it's kind of a lot, 18 different possibilities. It's sort of a lot, but it's not very interesting if you just go through if you go through one test case and try to go all the way through. It's kind of hard for all the possibilities. So you got to do more than one, but even this is like the smallest one I can go through. I can go through by hand. 7, 13, 22. So we have 6 and 22, which becomes 16. And then 13 and 15, which goes to 2. And then 7 and 9, which goes to 2. Yeah, 22 minus 13 is, while I'm doing this, I should keep this open. 22, yeah. So, okay. All right, so yeah, so I end up with the differences I can get are 2, 16, 28, and 42. Those are the only differences I can get at the end. It's pretty interesting. There's only 4 possibilities. Huh. That's weird. And 2 shows up the most. 2 shows up 1, 2, 3, 4, 5, 6, 7, 8 times. 8 out of half the time is 2. 16 is 4 out of what is this? 3, 6, 9, 18. Out of 18, I've got 9 out of 18. No. 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 18 is 2. 16 is 1, 2, 3, 4. 4 out of 6. 4 out of 18. 28 is 1, 2, 3, 4. 4 out of 18. And then 1 out of 18 is, no, 2 out of 18 is 42. Is that right? So we got, no, that's not right. I'm missing something here. What's the frequency? It's 1, 2, 3, 4, 5, 6, 7, 8. 8 times out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, it is 8 out of 18. 16 is 1, 2, 3, 4, 4 out of 18. 28 is 1, 2, 3, 4 out of 18. And 42 is 1, 2 out of 18. Why is this? This is only, okay, no, that's right. That's fine. Yeah. That's 8, that adds up to 18. Okay, for some reason. So interestingly, the smaller one pops up more than the other ones do, which is a little weird to think about. I'm wondering if there's something to that, actually. But yeah, there's quite a few ways to get 2. And all the other ones are, and these are kind of interesting. Like it's between 2 and 16 is 14. Between 16 and 28 is 12. And then 42 and 28 is 14 again. 14, 12, 14. Which the difference between 14 and 12 is 2. I don't think that's an accident, also. Very interesting. How did I get 42? 42 came from combining down 35, 35, 22, and 7 to make it very small, and then subtract that from 48. So I get 20, 15 minus 2, 13 minus 7 is 6. Yeah. So that seems to be the way to maximize, is to take your largest element, stick it off to the side, and then recurse basically on the other elements. Get those to be as small as possible, and then subtract that from the largest element. That'll give you the largest difference. To get the smallest difference, there's a few different ways to do it, it seems. And actually, I was able to get that 6 and 48 2 different ways. Maybe memoization is the way to go here. So how many of these are duplicates is a good question. So yeah, that might be, maybe that's it. Maybe I should just use memoization, and that's what I should do. Because there were only 4 solutions at the end of this anyway. And quite a few of these gave me the same solution. So 6, 48, yeah, 6 and 48. So I was able to get to 6 out of those other 3 by, I could either just subtract 7 and 22 from 35, or, excuse me, I can subtract 7 from 35, 7 from 35 first, or 22 from 35 first. But basically subtracting them both from 35, both of those options gives me the same thing. So yeah, the order of operations, basically that's why I was able to get both of those, because those 2 are the same order of operations. Excuse me. Same idea, but just different order of operations. So the ways that I got to 2 weren't that many. So how many of them were the same? So I got 7, 9 took me to 2 in 2 different ways. And 13 to 15 took me to 2 also in two different ways. So 7, 9, 13, 15, and then it was 26, 28, and 33. 35. 1, 2, 3, 4, 5, 6, 7, 8. Oh, wait. And there's 20 and 22 was one way. So I got me 2 in one way, but there's one more. 20, 22, 20, 26, 28 was two ways. Twice. Yeah, so that's kind of interesting. Getting back to what I was saying about memoizing, almost half of those were duplicated. But those are kind of peculiar. Those seem all kind of unique and all different, how I got to each one. Hmm. Okay. 7, 9, 2 and 2, or 7, yeah, 7, 9. And 13, 15. 26 and 28. 33 and 35. And 20 and 22. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right. Question is, what the question is, how did I get to each of those? So I got the 7, so from 7, 22, 35, 48. I got the 7 and 9 by going first to 7, 26, and 35. Which means I subtracted 22 from 48. And then I subtracted 26 from 35 to get 9. Then I got 2. Okay. But I got there in 8 different ways. I could have also first subtracted so subtracting 26 from 4. How else did I get to 7 and 9? I got to exactly 7 and 9 another way too. 7, 13, and 22. Could have alternatively gone to 7, 13, and 22 by subtracting 22 and 35 first. That would put me at 13 and 22. And then I got 7 and 9 again by 13 and 22. But that's really interesting. So yeah, I mean, the 7 was just untouched, right? I basically just got down to 9 from the right side, that subset. I mean, I could recurse on a subset with one less element and just get to the thing that gets me as close to the first element as possible. Interesting. Huh. You know what? I think I could do this in quadratic time with a DP. Maybe? No. Yeah, I don't know. I'm not too sure. I can modify this slightly and give it another parameter. Instead of f of some array, I could do g of an array with a target, right? And then I can say, then I actually don't need the array. I could just do g of some index and a target. And the targets are going to be between 1 and 100. And the indices are going to be between 1 to n, which is between 1 to 30. So that would give me 30 by 100 dp, which is only 3,000, which is doable. That might be the way to go. And with a target, makes things a little bit easier. That function is maybe easier to think about. Now that's a clever way to approach this. That's a clever way to approach this. With a target, what you can do is say, given some sequence of numbers, so 7, 22, 35, 48, I'm going to perform that sequence of actions as mentioned with a target 0, right? So my index would be, this would be f, then becomes f of this array, then becomes g of 0, 0, right? And the target is 0. And what I'm going to do is when I recurse, I'm going to recurse with 22, 35, 48, and the target is 7, right? So now I'm going to try to find now this could be maybe O of n squared times k, where k is 100, right, where it's a constant in this case. That would still be efficient enough. That would still be pretty fast. It would be, 30 squared is 900, and 900 times 100 is 90. I think 900,000. Let's see, I think I got this wrong before. I did 500 squared is 1, 2, 3, 4 with a 25. It's 250,000, not 25,000. I said it was 25,000 in another video on accident, which was a mistake. But 900 times 100 is 9 times 100 squared, which is 9 times 10,000, which is 90,000. Not 900,000. And 900 times 1,000 would be 900,000. It's 90,000. That's still efficient. This could be, no, I don't know if that's correct though, to do it cubic n squared times k. I don't know. I'm not sure, but what I'm looking for now is the solution that's closest to 7 among the other possibilities, right? And the next thing I would be looking for would be the solution that's closest from 35 to 48 to well, the target would be 22, I suppose. Is it necessarily 22? Actually, I don't know. This goes kind of fast, right? So that means g of 0, 0 is going to be exactly g of 1, 7. Which, what is g of 1, 7 then? Well, I don't really know. Well, the solution 22, 35, and 48, I mean, those could be only so many possibilities, right? You get it's only six options there, right? Really, 3 options, excuse me. 22 and 48 is 26 and 35, and then you have 22 and 35 is 13 and 48. And then 35 and 48 is 13 and 22. And each of those gives me 9, 9, and 35. Okay, I think the third case, A, B, and C, has a very clear solution. Well, every time. When you sort it, I think actually that's maybe the 3 cases very straightforward. Excuse me. Yeah, 3 element. Maybe I could do this by induction. Actually, I can maybe prove by induction what the solution should be. I don't know. Maybe. Okay. So the value that's closest to 7 is 9 in those cases. And g of 0, 0 is going to be g of 1, 7 minus 7. But how do you calculate 1, 7? Well, yeah, I don't really know. You'd want to calculate all of the, not really. Yeah, I don't actually know. Given a certain target, how do you calculate this? I don't know. That's a good question. But what's g of x, y, or alpha, beta? What is that though? With respect to other g values, I don't really know. It doesn't actually help that much, does it? No, it doesn't. No, not really. No. Gee. Oh. Yeah, I don't know. Anyway, if we look at A, B, and C, if it's sorted, again, we have only so many options. You have 3 possibilities. C minus A, B, B minus A, C, and then C minus B and A. C minus B and A, which it's not clear which of these is larger. And then of those options, you have B minus C minus A, absolute value, and then C minus B minus A, absolute value, and then A minus C minus B, absolute value, right? Which would then be b minus c plus a, c minus b plus a, and a minus c plus b. Okay. Interesting. Which gives me a plus b minus c absolute value, a plus c minus b absolute value, and a plus b minus c absolute value. Which is the same thing twice, a plus b minus c twice. And then a plus c minus b. So yeah, you only really have two options when a, b, and c are sorted. It's either, and that's a is always a positive value. Let's say a plus b minus c. If that's greater than or equal to 0, that's a plus b minus c. If it's less than 0, then the absolute value is the negation of that, which is going to be negative a plus negative b plus c. So it's a plus b minus c, or c minus a plus b. In the other direction, a plus c minus b greater than or equal to 0 gives you a plus c minus b. And then negated gives me, right, when it's less than 0. B minus a plus c. Okay. Which this is greater than or equal to 0, and this is greater than or equal to 0. That's greater than or equal to 0, and that's greater than or equal to 0. Okay. The thing is, b is never greater than a plus c. Meaning, the second case, a plus c minus b being less than 0 is never a possibility. Because c minus b is greater than 0. Greater than or equal to 0, which implies that a plus c minus b is greater than or equal to 0. Okay. So that one, a plus c minus b, does not have to be an absolute value. That's just a plus c minus b. The other case, however, a plus b minus c, I think that does have to be absolute value. That one's a little more complicated because a plus b could be smaller than c, in which case that would be negative. On the other hand, a plus b could be larger than c, in which case this is positive. A plus c, though, is always larger than b, because c is always larger than b. Okay, interesting. So which one's smaller? A plus b minus c absolute value, or a plus c minus b? Well, a plus b minus c, or c minus a plus b, or a plus c minus b. Okay, well, a plus c minus b is always greater than or equal to a. That's number one. And that seems like it's probably the largest value. And a plus b minus c is always going to be less than a. Because b minus c is less than or equal to 0. C minus b minus a, on the other hand, that could also be larger than a. Because c could be large, it could be larger than, could be way larger, unbounded. C could be unbounded in size. So c is unbounded in size, but that you have to compare that to c plus a minus b, right? So you have c minus b minus a, c minus a minus b, and c plus a minus b, if c is very large. If c is small, then you have negative c plus a plus b. That's confusing. Let's look at it. If a plus b minus c is greater than or equal to 0, then a plus b is greater than or equal to c, and then what does that imply about a plus c minus b? Well, a plus b minus c as compared to a minus b plus c, right? Since c is greater than b, that implies that adding c and subtracting b, so c minus b is going to be greater than or equal to 0, whereas b minus c is less than 0. So that means that a plus b minus c is less than a minus b plus c in absolute value, right? So that's going to be a plus b minus c. If that's greater than or equal to 0, a plus b minus c is going to be the larger of the two, or smaller of the two. If, on the other hand, it's smaller, right? Excuse me, so a plus b minus c absolute value and a minus b plus c. Suppose a plus b minus c is greater than or equal to 0, then that implies that a plus b minus c is less than or equal to a minus b plus c, right? Because this minus b, you could say a plus b minus c minus 2b minus 2c or something. I don't know how to say that exactly. You can add b to both sides, get a plus and c to both sides. A plus 2b plus 2c is or excuse me, a plus 2b is less than or equal to a plus 2c, which you have 2b is less than or equal to 2c, which you have b is less than or equal to c, which is true. So you can go upwards. B is less than or equal to c, then 2b is less than or equal to 2c, then a plus 2b is less than or equal to a plus 2c, and then you could subtract b and c from both sides to get that a plus b minus c is less than or equal to a minus c plus b, or a minus b plus c. Now again, this is if a plus b minus c is positive, right? If it's not greater than or equal to 0. If it's negative, things get a little bit more complicated. Is the absolute value, which is then going to be c minus a plus b, is that less than or equal to a minus b plus c? So that would be negative a plus negative b plus c. Is that less than or equal to a minus b plus c? Okay. In this case, I would say, yeah, it's also true. Because negative a plus negative b plus c, or you can add on both sides a and b again, or really, yeah, add on both sides a and b, and you get negative b plus c is less than or equal to 2a plus c. I don't know. Actually, adding a plus b on both sides gives me, yeah, c is less than or equal to 2a plus c, which is true, right? 0 is less than or equal to 2a, which is a is less than or equal to 2. A is greater than or equal to 0 is true. So yes, you can show that if a plus b minus c is less than 0, then you want to get the negation of that, which is c minus a plus b, and that c minus a plus b is always going to be less than a minus b plus c. So in both cases, it's going to be the absolute value of a plus b minus c. Okay, so if it's only 3 elements, always going to take the largest element minus the sum of those 2 smaller elements and take the absolute value of that. All right, that's interesting. I don't know if that's the case in all scenarios here. But yeah, if we got rid of one element here, just said if I think that's, let's see. It's good to not make typos. Okay, I think that's correct in all cases where you have 3 elements. Oh, okay. Let's try some random similar test cases. Oh yeah, I went too far with this one. Okay. Yeah, nice. Now the question is, what if I just took, like, does this extend to the 4th case, right? So what about A, B, C, and D? Well, 4 possibilities with A, B, C, and D. There's 6 different possibilities, right? A, B, A, C, A, D, B, C, B, D, and then C, D. So A, B would be B minus A, C, D. A, C is C, A, B, D. And D minus A, B, C. And then finally, b minus c minus b. C minus b is AD, and D minus B is AC, and D minus C. Okay, so question is, each of these have one result, which is going to be, I don't know which one of these is necessarily the largest. Well, B minus A is definitely going to be smaller than C and D, so D is the largest here. So here it's going to be the two smaller ones minus the larger one, absolute value, right? So it's going to be B minus A plus C minus D, absolute value. Next is going to be C minus A may or may not be larger than B, but it's definitely smaller than D. Right? There's three possibilities here that are definitely smaller than D. So there's, again, negative A plus B plus C. So this is negative A plus B plus C. It's actually the same thing. Minus D, absolute value. Which just gives me negative A plus B plus C minus D. Minus D, excuse me. These are actually the same thing twice. Absolute value. Now it's not clear to me which one is larger in the other cases. We'll come back to that in a moment. But half of these cases where D is definitely the largest, and the other two numbers therefore must be smaller. You add them together, you get, so here we have A minus B plus C minus D, absolute value. So that's actually different. So one is negative A plus B plus C minus D. Another one is positive A minus B plus C minus D. Absolute value of these things. One of these is definitely smaller or larger than the other, I'm sure. And then D minus A, B, and C, D minus B, A, and C, D minus C, A, and B. It's not clear which numbers are the largest ones in those cases. Those definitely have, depending on what the order is, those definitely have a clear solution. But it depends on what the order is. I don't know. I don't know. So D minus A compared to B and C, that could be larger than B and C. That could be between B and C, and that could be smaller than B. Let's see. It's not really clear which one it's going to be. Oh man. Oh man. Gee. Excuse me. Oh. I think one way to think about this is to consider A, B, and C such that you have minus A plus B plus C, or plus A minus B plus C, or plus A plus B minus C, or you have minus A minus B plus C, or you have minus A minus B minus C, or all those different possibilities, right? There's 2 raised to the n different ways to try these different possibilities. But the reason I suggest that is each of these are a choice, right? Either negative A or positive A, and then negative B or positive B, or negative C and positive C. Which I missed a couple there, but that's fine. And what's interesting about that idea is that now you could I think you can do this using dynamic programming and do this in linear time. Because you would say, well, I could either add A or subtract A, right? And I want the of those options, I want, F is of, B, C, etc., and F of, same thing. But I want the of those 2 options, I want the smallest absolute value, right? And it would be the minimum of A plus, F of I plus 1, basically, and negative A plus F of I plus 1, and both of those absolute value. The problem with that, though, is it's not necessarily F. We'll call it G and F. Because I want to make I want A plus, I think it's A plus G of I plus 1 in A is really what I want. And same thing, negative A plus G of I plus 1 negative A. Or positive A. Meaning, for each of these values, I want the sum to be as well, the first one should be negative. Actually, the first one should be as close to negative A as humanly possible, and the other one is going to be as close to A as humanly possible. Because actually, I can get negative values from these summations, so it's not really recursion exactly. So I'm not going to return the minimum. I'm going to return whichever one. Well, whichever one is closest to the target is actually what I want. And that's the number I want to return. So if there's some target value, and I want to be as close to that target value as I can get, then I'm going to take the minimum of the absolute value of the difference between the target and I guess A plus G of I plus 1 negative A, something. That's really confusing. That's really confusing. And the number itself, I think I want what I return is I don't even know what I return. I have no idea. That's so confusing. I don't know. I think I could do this with DP, but definitely not obvious how. Really not obvious how. Yeah, so I guess what I'm trying to say is that the different values could be either, excuse me, all negative or all, they basically switch in parity. The final sum I'm looking for is basically like whatever summation I have I'm looking at, it's the sum over all the elements, with, depending on how you do it, each element either being positive or negative, right? That's basically what it boils down to, is that each element is either positive or negative that's being added together. And so I'm looking for the correct choices of positive and negative values that give me the smallest absolute value. Excuse me. Yeah. The smallest absolute value. Which is very confusing. Which is confusing. Not necessarily looking for the smallest value, because the smallest value could be negative. In fact, the smallest value would be all negative numbers. So it's the smallest absolute value of the sum, with positive and negative numbers considered. Okay, I think it's pretty close. The only two options that aren't possible would be, I think, would be all positive and all negative, which in both cases those would actually be those would always be excluded anyway, because those absolute values would be always larger than everything else anyhow. So yeah, in that case you could take, now what's interesting is each number is positive, right? Well, yeah, it could be positive or negative, right? And so I'm not sure if my return value, if I'm just going to try to do this recursively, and my return value is just always going to be the smallest absolute value, then it's possible that I get a positive absolute value and then a positive number and a negative number. And technically I could do either one, because I could just flip all of my signs to give me the negative one if I need it. So if I have a is a negative number and I add a positive number to it, that'll make it smaller. And then if a is a positive number and I add a positive number to it, that'll make it larger, so I'd want to add a negative number. And even the absolute value of that would be still a smaller absolute value. That's kind of what I'm getting stuck on. That's kind of what I was getting stuck on. But yeah, in that case you could do a, it's the absolute value of a minus f of sort of I plus 1. And that's one option. The other option is negative a plus f of I plus 1, where f of I plus 1 is always going to be a positive number. And negative a minus f of I, the absolute value of that is always going to be larger than the absolute value of negative a plus f of I. And similarly, the absolute value of a plus f of I is always going to be smaller than a minus f of I, or larger than a of f of I. So I don't have to check those two possibilities, but those two possibilities also could exist. It's kind of what I was getting confused about. So I think that's it, actually. That's actually very straightforward. And yeah. Yeah, I think it's just, I think it's that simple. The minimum of the absolute values of that. Is that it? That's actually very efficient. if I DP on that, it's actually a could do top-down memoized recursion, but actually can DP in the other direction too. I think you could use DP with this. It's confusing, but it can be done. It's not obvious at all. Man, these questions are tough. I'm assuming I get it right. These questions are tough. Yeah, so let's do top-down memoized recursion. Try that, and then I'll DP. Okay. What am I going to return here? What I'm going to return is, I think, just the result. Yeah. What's it? It's 100 times 30 is like, we'll do 5,000, or let's do 10, or yeah, 10,000. All right. Yeah. Well. Okay. Yeah, I could definitely just do a straight DP too. I think. We'll come back to this. Come back to it. So int ix. And we're gonna say turn v of ix plus f negative ix. So positive vix will subtract negative vx, will add if. Come back to that in a moment. So it's going to be the minimum of these two, absolute value of these two. Okay. And we're going to say if ix equals n minus 1, just return the ix as it is. Could be negative, it could be positive. Yeah, I think a single element, you just return it. I think that's fine. And this is just ix plus 1. I think that's correct. Is that it? Is that the whole thing? I don't know. Wrong. Oh. Forgot the DP. I don't know if I even need to DP, quite frankly. Well, maybe I do. I don't know. I have no idea. This is confusing. I don't know if I even need, this is like, not sure about this one. I don't know if I even need I don't know, DP array. Just correct in all cases, of course it is. I don't know. Let's try this. Okay, it's wrong in some cases. We got 3, this should be 1. 15 should be 5. Okay. It's correct in some cases, but wrong in others. Yeah, I mean, gee, I don't. Could be positive or negative. Yeah, well, okay. I mean, yeah, literally it could just be a loop. It was a little strange. It's a little strange how I've decided to do this. Actually, this is really odd how this works. You know, I'm not too sure about this. What is going on? Huh. Okay, it's definitely not this simple, this one. Yeah, this is not correct, but it's getting closer. Let me not get rid of this completely. Get rid of some of it, but not all of it. So this is not the right answer, but it's an interesting idea. Correct in some cases. A little bit off. The problem is I think I need something a little more sophisticated. I just need a target. Okay. And what I'm going to say is something like the following. So what I'm going to return is, given a particular target, the sum that is closest to that target, right? Yeah. So possibilities. And the sum that's closest to that target is going to be let's use optionals here. Yeah, okay. So now it's memoized. It wasn't memoized before. Okay. So I want an x plus 1. I don't know if this works. I don't think this makes sense. So we have a value, which is going to be v of ix, call it a. And we're going to say, okay, okay, so this return value is going to be the absolute value of the difference. Because if vix is positive, target minus that value, if vix is much larger than the target, then this difference is a negative value. And yes, so this basically decides whether or not it's positive vix or negative vix. So if it's negative vix, that means the target is much larger than vix. Or is larger than, oh, whoops, whoa. this basically will decide whether or not it should be positive or negative, and it'll return. What's interesting about this though is it's going to return the value closest to the target, absolute value that's closest to the target. I'm trying to figure that out. Should I return? What do I return here? Do I return the value closest to the target, which is just VIX every time? Or do I return like plus or minus VIX or the value? That's the part that's confusing. There's only, yeah, well, it's always going to give me return the standard absolute value. Okay. Yeah, that's fine. That's fine. No matter what the target is, doesn't matter. Now let's say we have a target and we say, all right, I want to get I could either have negative A or positive A, right? And add to that some recursion, right? And so if my target is, let's say my target is 10, and I've got, 3, 7, or actually it doesn't have to be sorted, but it's 7, 3, and 13, right? I want to know the sequences of plus and minus values for 7, 3, and 13. It'll get me closest to 10. That means if I take the difference between I don't necessarily know what the target should be for 7, 3, and 13 though. That's confusing. That's really confusing. Well, I know what my options are, right? There's a few different possibilities. 7, kind of went through that before, what the possibilities are, but it's basically plus or minus 7, plus or minus 3, and plus or minus 13 is what I want to consider. So we have 7 plus 3 plus 13, 7 plus 3 minus 13, 7 minus 3 plus 13, 7 minus 3 minus 13, negative 7 plus 3 plus 13, negative 7 plus 3 minus 13, and then negative 7 minus 3 minus 13. This should be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 should be, yeah, so negative 7 minus 3 plus 13, and then negative 7 minus 3 minus 13. Okay, those are all the possible values I can come up with, and I get 23 on one of them. I get negative 3 on another one. I get 17 on another. I get negative 9 on another one. I get 19 on another one. And I get negative 17 on another one. I get 3 on another one. And I get negative 23 on another one. Okay. Alrighty. And then the absolute value of all these gives me 23, 3, 17, 9, 19, 17, 3, and 23. Okay. So these are duplicates, right? So the one that's closest to 10, so it's 3, 9, 3, 9, 17, 19, 23. All right, fair enough. Okay, the one that's closest to 10 is going to be 10 minus 9 is 1. And 10 minus 17, absolute value, both of these is going to be 7. But so the one that's absolutely closest is 9. So I would want to return 9 for this function. And that's fine. How can I calculate that? Well, I have +7 and I have -7. And I'm looking at 3 and 13 in both of those cases afterwards. And I have this function that can take a target for 3 and 13. Tell me what's the target I want for 3 and 13. I don't actually know what some will call it T sub I and T sub J, or some, I don't know, some alpha and beta targets. I don't know what those are supposed to be. Maybe I can go through all of the targets? I have no idea. Hmm. Oh, this is tough. I don't know. I'm gonna take the headset off and just lay down for a minute. I don't know. It's confusing. This is confusing. I'm not really understanding exactly what I need to do here. It's not seeing it. I know I'm very close, but it's a little more complicated, I think, than I'm giving it credit, or something. Something's not quite right. Oh yeah, of course I can go through. Excuse me, I can go through every possible sequence, but it's not quite right. It's not exactly obvious how to do this. Let's phrase it that way. All right, I'm just gonna sit and think about this for a while. I don't have an answer. Don't have an answer. Okay. So one of the benefits of living back at home is mom makes food every now and then. So I can go get some food. This is a tough question. Yeah, I'm still thinking about it. I might just make this a part 1 and come back to it in a few minutes. Come back to it later. Go down, go get some food, come back. Or I don't know. I might just leave the stream on. I have to decide what to do. I'll give it a minute here. Let me just keep thinking. Okay, I think I got it. So since I believe you can get any sequence of plus or minus values, and you're trying to get the minimum absolute value of the sum over that sequence, you could take this to mean break the values into two subsets, and we're looking for the subset sum such that the larger sum minus the smaller sum is as small as possible. And so another way of doing this is to look at the sum of all the values divided by 2, and we're looking for the subset. There really should be two subsets. Two subsets that are as close as possible to that number. Looking for a subset sum that's as close as possible to that number. And the other subset would be the complement. And you take the difference between those two subsets, and because they're both as close as possible to the midpoint, their difference is guaranteed to be the smallest difference, which just means it's going to be the desired result. So basically take some number of values that when you sum them gets as close as possible to the midpoint. Again, fortunately, these numbers are there's only 30 times 100 is 3,000. So I think I can actually memoize on somehow. I'm pretty sure I can use like some kind of memoization to get this efficiently. Not exactly sure how I'm going to do it though. But yeah, let me come back to it. Let me make this a part 1 and then take a break, go to the bathroom, get some food, hang out for a bit, and then come back and make a part 2. But I'm pretty sure it's got something to do with trying to get as close as possible, some kind of memoization to get as close as possible to the midpoint sum. Yeah, there aren't that many possible sums I can get. So, yeah. And yeah, I can have a target sum. I could do it that way. That works. That works. I could have a target sum that's bounded by 3,000 and dp over that, and then just either add the element or not add the element. And the target sum should be the sum divided by 2. And basically just try to get as close as possible to that target. Um, I'm not sure. Not sure. So it's something like this is what we're looking for. I don't know exactly. Again, I think these numbers are small enough where I should be able to achieve this using some kind of memoization. I mean, the actual sums that are possible are there's only 3,000 of them, so I don't know how exactly I can make use of that, but I'm pretty sure that allows me to do this efficiently. I just kind of have to think a little bit harder about how I can make use of that to get the answer and to do it. Yeah, use some kind of memoization. So yeah, okay, that's pretty tough. It's a tough question. I don't know what to say. I'll keep trying. Keep thinking about it. Let me make this part one, and then stop the stream and come back. Make this part one. Stop the stream and come back to this later. Take a break. It's a hard question. It's a hard question. Tough question. Yeah. All right. So yeah, thanks for watching. Talk to you soon. Take care.